Hi guys, so today we're going to transition. Instead of looking at specifically the cubic parent function and its transformations, we're going to look at just polynomial graphs in general. Now x cubed is an example of a polynomial, but it's one of many polynomials that are out there. So what a polynomial is, it's actually a lot of things you guys have already seen. Y equals x minus 2 is a polynomial. Y equals x squared minus 2 is a polynomial. Y equals x cubed minus 2 is a polynomial. Polynomials, they have a couple of characteristics. First of all the exponents are whole numbers. We do not have any variables in the denominator, no variables under a radical, and the graphs are continuous with no sharp turns or holes. That means that absolute value is not a polynomial because it has a sharp turn. It comes to that point. So some things that are not polynomials, okay, some things that do not fit those characteristics. 1 over x is not a polynomial. X to the 1/2 is not a polynomial. 3 to the x is not a polynomial. Or the square root of x is not a polynomial. Now, you can have radicals, you just can't have the variable under a radical. So the square root of 7 times x cubed minus 3x squared plus 1/4, that's okay. That is a polynomial because it's about the variables. But if you have a variable that fits one of those characteristics, then it may not necessarily be a polynomial. So the degree of a polynomial is something we're going to talk a lot about today and over the next couple days. So the degree is the highest exponent when your graph is, or when your equation is written in standard form. Now in standard form, that has basically your terms in order with the highest exponent first. So for example, let's say I have the function 3x cubed minus 7x squared plus 4x minus 2. That is in standard form because your exponents go from highest to lowest. Intercept form, on the other hand, is basically factored. And the reason we like intercept form is it makes the x-intercepts really easy to see. Now we're going to look at both of these today. Now, once we find the degree, we're going to use it for a couple of things. One characteristic of the degree is that one less than the degree is the most possible number of turns your graph can have. And your turns, if you remember, those are your relative extrema, your relative mins and your relative maxes, or absolute mins or maxes, depending on the function. All right, so let's talk about... All right, so to find the degree, we're going to start by writing it in standard form. Well, example 1, that first one, that already is in standard form. My exponents go from highest to lowest. So the highest exponent there is 5. That means that degree is 5. Well, if the degree is 5, that means the most turns that this graph could possibly have, we should write max number of terms, sorry, is 4. Now, it could have less than 4, but the most turns that it could possibly have is 4. Now, some other things we're going to do is we're going to identify the polynomial by the number of terms and the degree. So since the degree is 5, that actually has a special name. If the degree is 2, it's quadratic. If the degree is 3, it's cubic. If the degree is 4, that's called quartic. And if the degree is 5, that's actually called quintic. Now, the name for the 4 and 5 is not really as important, but we also want to be able to identify it by the number of terms. So terms are the things that are being added or subtracted. This graph has 3 terms, so we would consider this graph to be a trinomial. And this is just some terminology you're going to hear me use a lot, which is why I want to get used to writing it down now. All right, let's look at B. B is not in standard form, so I'm going to reorder it. Okay, so now it's in standard form. Degree here, biggest exponent, is 4. That means the max turns this graph could have is 3. Since it's 4th degree, we would call that quartic. And because, again, there were 3 terms, there were 3 things being added or subtracted, that is a trinomial. All right, now looking at C. C is not in standard form. C is an example of intercept form. Now, without multiplying this out and writing it in standard form, we're still able to determine the degree, and that's something we're going to do a lot, so we need to be used to that. So if you think about this, before we FOIL it out, if this were multiplied out, I would have x squared times x to the first times x to the first. That means the biggest exponent here would be x to the fourth power. So this is going to be a degree 4. Now just for practice, I am going to go ahead and FOIL this out because this is something we're going to look at next class. So x minus 2 squared, remember that actually means x minus 2 times x minus 2. So if I multiply that out, I get x squared minus 4x plus 4. If I multiply x plus 1 times x minus 7, I get x squared minus 6x minus 7. Then if I go ahead and FOIL out this whole thing, it's kind of messy, so you're not going to have to really do this for graphing, but this is good practice for what we're going to do next class. And then we get our whole big polynomial there. We combine like terms. Oops. Nope, that is right, sorry. And now we're in standard form. Again, we could tell the degree without it, but I just want to make sure that you guys realize there's a difference between standard form and intercept form. So be careful when you're finding the degree. So again, to answer those questions, the degree here would be 4. That means the max turns is 3. This graph, again, there's not really a good name for it, is quartic, but again, we need to know how many terms. There are 1, 2, 3, 4, 5 terms. So this is a 5-term polynomial. And that's just another way we can classify it. All right, so let's go ahead and look at what effect the degree actually has on the graph. The reason it's important for us to be able to determine what the degree is because if that number is odd or even, it helps us to determine the end behavior of our polynomial. So we've talked about end behavior a lot this year. So now, until this point, you've always been given the graph, though, and you've had to determine the end behavior from the graph. What we're going to do now is determine the end behavior from an equation, and that's going to be based on 2 things. We're going to look at the leading coefficient to determine if it's positive or negative, and we're going to look at the degree and determine if the degree is odd or even. Now, the leading coefficient is just the coefficient of the highest powered term. So back to the previous example. Oops, sorry about that. If we look back at my previous example, the leading coefficient for A is 3. The leading coefficient for B is 2. The leading coefficient for C, if this was all multiplied out, would be 1. So that's what the leading coefficient is. And again, what matters for that is whether or not that's a positive or negative number. So we have 4 possible cases here. We can have a positive leading coefficient with an odd degree, a positive leading coefficient with an even degree, or a negative leading coefficient with either an odd or an even degree. So this little chart here is going to help us remember this, but what's easiest to do actually is to think about some basic parent functions that you already know that fit these characteristics. So for example, an odd degree polynomial with a positive leading coefficient. The simplest graph that meets that criteria is y equals x, and we all know what y equals x looks like. So the ends of every positive leading coefficient odd degree polynomial are going to match the ends of y equals x. So as x approaches positive infinity, f of x approaches positive infinity. As x approaches negative infinity, f of x approaches negative infinity. So that's what the end behavior is if it's a positive leading coefficient in odd degree. All right, let's look at odd degree and negative leading coefficient. Well, the simplest function that meets that criteria is negative x. And again, we know what the ends of that graph look like. So even though the middle can do a bunch of different things that we'll get to in a minute, the ends are going to match that behavior. So as x approaches positive infinity, y approaches negative. As x approaches negative, y approaches positive. All right, now let's switch to even degree. The simplest even degree polynomial that you guys know is x squared. And again, the ends of y equals x squared are both going up towards positive infinity. So every even degree polynomial with a positive leading coefficient will also have its ends going up. All right, so in the last case, negative leading coefficient, even degree, think of y equals negative x squared. You know that graph has ends going down. So your end behavior is going to match that. All right, so the end behavior of a function, again, we just need to determine the leading coefficient and if the degree is odd or even. So let's look at example 2. To determine the end behavior, let's look first at the leading coefficient. Well, the leading coefficient is a negative number. Then let's look at the degree. The degree, the biggest exponent here, is 5. Negative leading coefficient, odd degree, means my ends will look like this. So then I'm going to write the end behavior that matches those arrows. As x approaches negative infinity, y approaches positive infinity. As x approaches positive infinity, y approaches negative infinity. All right, let's look at B. If this were all multiplied out, it is currently not in standard form. So if it were multiplied out, that leading coefficient would be positive. It would be a positive 1. The degree is not just the biggest exponent. We have to think, if this were multiplied out, this would be x to the 4th power. So the degree here is 4. So positive leading coefficient, even degree, my ends are going to look like this, which means as x approaches negative infinity, y will approach positive, and as x approaches positive infinity, y is approaching positive infinity. All right, so that's end behavior. So end behavior is the first step in sketching a polynomial graph. The second step is figuring out what does your graph do in the middle. And the biggest factor here is going to be the x-intercepts. So if your graph is not in intercept form, well, you're going to need to factor it to put it in intercept form. To start, though, we're going to look at some graphs that are already in intercept form. So what we're going to do is we're going to find the x-intercepts, and then we're going to see what our graph actually does at those points. So depending on the exponent of the factor, your graph can do a couple different things. So the exponent of a factor is called the multiplicity. That's just the number of times a factor or root repeats itself. So the multiplicity helps us determine what your graph does at that point. If the multiplicity is odd, your graph is going to cross the x-axis at that point. Now, how it crosses is going to be different based on what that number is. The bigger the number, the flatter it's going to get as it goes to that point. So basically, if the multiplicity is odd and it's a number larger than 1, instead of just crossing, we say it kind of wiggles. Because think about the difference between y equals x and y equals x cubed. Both of those have an x-intercept of 0. But y equals x just crosses straight through it. Whereas y equals x cubed, it kind of curves as it goes through that point. So we refer to that kind of as a wiggle. Because again, the multiplicity here, the exponent, is 3. Now, if that multiplicity is an even number, the graph is going to be tangent at that point, which means it's going to touch it and bounce back. So in order to sketch this graph, the first thing we're going to do, we're just going to list what the x-intercepts are and then what your graph is doing at those points. So the first thing is we're just list the x-intercepts. Well, this is already in factored form. So we'll just find the x-intercept that goes with each factor. Well, x gives us an x-intercept of 0. X plus 4 gives us negative 4. And x minus 3 gives us 3. So now to determine, this is just where your graph will touch or cross the x-axis. To determine what it does, we look at the multiplicity. The multiplicity, that is the exponent of that specific factor. So x is raised to the first power. That means the multiplicity of that factor is 1. X plus 4 is raised to the first power. That means the multiplicity of that factor is 1. X minus 3 is squared, which means the multiplicity of that factor is 2. Once we know what the multiplicity is, we can determine what our graph actually does at that point. So if the multiplicity is 1, our graph will cross. If the multiplicity is even, our graph is going to touch or bounce or be tangent. You can use any of those words. So this actually makes it really easy now to sketch our graph. The only other piece of information we need is our end behavior. Well, let's go ahead and review end behavior. This is a positive leading coefficient. The degree, if I add up all those exponents, would be 4, which is odd, or even, sorry about that. So if it's positive leading coefficient, even degrees, that means I'm going to be up and up. All right, so now I'm going to mark my intercepts. So this graph is going to have an intercept at 0, at -4, and at 3. So then to sketch my graph, I'm just going to do what my graph tells me to do at each of those points. At -4, it tells me to cross. So I'm going to cross at -4. At 0, it tells me to cross. So I'm going to cross at 0. At 3, it tells me to touch. So I'm going to bounce from that point back in the same direction. And one thing that's really nice about these graphs that you'll notice, the end behavior is always going to match up with what you have for your behavior at the x-intercepts. If it doesn't match up, you made a mistake somewhere. All right, let's go ahead and try the next one. We're going to start with the x-intercepts. So my x-intercepts would be 0, 7, and -6. Then let's find the multiplicity. That's the exponent of that specific factor. So that exponent was 5. This exponent is 2. This exponent is 1. Then because of those exponents, let's figure out what our graph will do at those points. If the exponent is 5, that's an odd number, but it's bigger than 1. So it's not just going to cross. Specifically, it's going to kind of flatten out or wiggle closer to that point. If the exponent is 2, your graph is going to touch at that point. The exponent was 1, so at that point your graph is going to cross. Now to sketch the graph, all we need is the end behavior. So this has a negative leading coefficient, and the overall degree would be 5, 6, 7, 8. So this would be an even degree, which means the ends of my graph will be down in both directions. Mark your x-intercepts. So I've got -6, 0, and 7. And then follow what your graph tells you to do. So my graph says at -6, I'm going to cross because the exponent of that factor was 1. So I'm going to cross through -6. At 0, the multiplicity was 5, so I'm going to wiggle. So it's going to still cross, but it's going to kind of bend as it goes through that point. Then the last intercept at 7, your graph is going to touch. So I'm going to go back and touch, and then end at my arrow. Now what's nice about these graphs is we're not going to be super specific with a lot of points outside of the x-intercept. How high and low those curves go, there's no way for you to determine that unless you use a graphing calculator. So if you don't have a calculator, you do not need to determine those values. If you don't have a calculator, what you need to look for is the end behavior, the y-intercept, but in this case we already had the y-intercept because it was 0. But if you don't know the y-intercept, plug in 0 and get your y-intercept. This is really easy to do when it's in standard form. Then we're going to find the x-intercepts, which we just did, and then find the behavior of the graph of the x-intercepts. And that is really all we need to do. The rest of, again, the specifics of where, how high and low those points go, we're not going to be able to get into that without a graphing calculator. All right, so let's look at a couple more examples. So these first ones are already in intercept form. So if you feel pretty comfortable, pause the video and try these ones on your own. All right, so I'm going to go ahead and start with end behavior, just because that's where my arrows are going to go. So this graph has a negative leading coefficient. And let's find the degree. Well, I have x cubed, I have x squared, and I have x to the first. So if you notice on this one, there isn't an x out here. So I don't need to worry about that because it doesn't have any x's associated with it. It's just the coefficient. So overall, the degree here would be 6, which is even, which means the ends of this graph are going to be pointing down. All right, let's go ahead and mark our intercepts. I have an intercept at 2. I have an intercept at 5. and I have an intercept at -1. Then all we need to do is determine what our graph does at those points. So again, at -1, that factor has a multiplicity of 1. So that means my graph is going to cross at that point. All right, then I get to 2. Multiplicity there is 3, which means at that point, my graph is going to wiggle. So it's going to bend a little bit, and that's kind of a bad drawing. So let me just try and kind of resketch that real quick, sorry. There. It kind of looks like y equals x cubed as it goes through it. All right, then we go to the last intercept, which is 5. That factor is squared, which means my graph is just going to touch at that point. And it goes back and bounces back towards my end behavior. All right, look at the next one. Positive leading coefficient. My degree, this one does have an x out in front, so this is going to be 2 plus 5 plus 1. So that's a degree of 8, so that is also an even degree. That means my ends are going to be pointing up on both sides. All right, let's find our x-intercepts. Those are 0, 1, and -2. Then to determine what your graph does at that point, look at the exponent of that factor. 0 is squared, so my graph is going to touch at 0. X minus 1 is raised to the 5th, so your graph is going to wiggle at that point. -2 is raised to the first power, so your graph is going to cross at that point. So let's mark those intercepts. And then just follow what we wrote down. At -2, I'm going to cross. At 0, I'm going to touch. And at 1, it's going to wiggle. And I don't need to go out that far. Could make it just go up here. I just drew my arrow there to make it a little bit easier to start the graph. But that's my picture. Again, how high and low those curves are is not as important. Now on A, if you wanted to find the y-intercept, you could. That's going to be a pretty large number. I would probably give you a 4-function calculator if I expect you to find that y-intercept. But you could plug in 0 and multiply those all together and figure out what that y-intercept, and you're going to notice it's a pretty large number. All right, now let's keep going. The last couple that we're going to graph, we have to factor first. It's still going to be the same process though. So to factor, to start, we're going to take out our GCF. X squared comes out. I'm left with x minus 2. So now, first of all, since I have the standard form, it's pretty easy to see the leading coefficient and degree. Highest exponent there was 3. Positive leading coefficient. It's going to be odd degree with a positive leading coefficient. Now that it's factored, I can see my zeros. My zeros are 0 and 2. 0 is squared, so my graph will touch at that point. X minus 2 is raised to the first power, so my graph is going to cross at that point. Because this is a positive leading coefficient in odd degree, my ends look like y equals x. So my graph is going to touch and cross, and then I'm done. Now one other thing just to keep in mind when you're drawing these graphs, remember we said there's no sharp turns, so all of these are really curves, and I know sometimes it may be hard to tell just on the iPad, but all of these graphs are going to be curved as they go through those points. All right, let's go to D. Again, we need a factor, so let's take out our GCF. Well, I can take out a negative x cubed from both of those terms. That would leave me with x minus 2. So then from there, it's clear to see your x-intercepts are 0 and 2. 0 has a multiplicity of 3, so it's going to wiggle. 2 has a multiplicity of 1, so it's going to cross. If you look at the original and standard form, it's pretty easy to tell your leading coefficient is negative and your degree is even because it's 4. So negative leading coefficient, even degree, my ends will be pointing down. Y-intercepts are 0 and 2, or sorry, x-intercepts are 0 and 2. At 0, my graph is going to wiggle, and at 2, my graph is going to cross. All right, last two, again, was just factor first. start with our GCF. So all three terms have an x. Then to factor this, I need to find what numbers multiply to negative 18 and add to a negative 3. Because a is greater than 1, I now have to split up my middle into those two numbers. Then I'll do grouping. 2x comes out. 3 comes out. The x minus 3's are shared, and now my thing is fully factored. From here I can find my intercepts, 0, negative 3/2, and 3. All of those are raised to the first power, which means all of those are just going to cross. So let's go ahead and mark our intercepts. Let's find our end behavior. This was an odd degree and a positive leading coefficient. So I'm going to go up to the right, I'm going to go down to the left, and I'm going to cross through all those points. All right, last one, we're just going to factor. On this one, I need numbers that multiply to 36 and add to a negative 13. Those are negative 9 and negative 4. So I'm going to split up my middle and keep my terms consistent. So this is going to become x squared comes out. X squared minus 9 is shared. And now you'll notice both of those are difference of squares. So that'll factor into x plus 3, x minus 3, and x plus 2, x minus 2. So now again, it's very easy to see our intercepts. Negative 3, 3, negative 2, and 2. All of them have multiplicities of 1, so all of them are going to cross. End behavior, positive leading coefficient, even degree. So this graph is going to end up. And then what's really nice about this is if you want to find that y-intercept, it's really easy to do. Because if I plug in 0 into my original equation, well, 0 to the 4th is 0, minus 13 times 0 squared is 0, so the y-intercept is just that c value. So my y-intercept is just 36. So if you want to mark that in your graph to make it more specific, that's a good other thing to add. All right, so the last thing we're going to do is we're going to look at just some characteristics. So this is just reviewing some of the things we've already talked about. So this graph is tells us where this graph is increasing, where this graph is decreasing. It says f of x is greater than 0 on that interval. F of x is less than 0 on those intervals. Remember, if your function is greater than 0, that's another way of saying your graph is positive. If your graph is less than 0, that's another way of saying your graph is negative. Well, the only way your graph can change between positive and negative is if it crosses the x-axis. So these points right here are the x-intercepts. And remember, when we talk about intervals, those are listing x values. So it's saying from the x value of negative 2 to the x value of 3. So where it changes, negative 2, 3, and 5, those are my x-intercepts. So this graph is going to have x-intercepts at negative 2, at 3, and at 5. All right, what we also know now is where it's positive and negative. So I'm just going to shade to help me figure that out. Between negative 2 and 3, my graph is positive. Between 5 and infinity, my graph is positive. Between negative infinity and negative 2, my graph is negative. And between 3 and 5, my graph is negative. So now, I need to figure out where my graph turns. Well, remember, where your graph changes from increasing to decreasing, those are your relative mins and maxes. That means that 0 and 4 are going to be the locations of your relative mins and maxes. So 0 and 4 are the x values where those are happening. So if I go to the x value of 0, the y value I choose doesn't matter as long as I put it in the right positive or negative region. Well, I shaded in the positive part there, so it needs to be somewhere in here. Again, the y value can be anything, but it does have to be positive. The next place it's going to turn is 4. So it changes from increasing to decreasing at 4. At 4, my graph is negative, so I'm going to pick some value in that region. Then from this point, I'm just going to sketch a graph. Since it's a polynomial, it should be kind of that smooth, continuous curve with no sharp turns. And now I have a graph that meets these criteria. It says using the graph, we're going to describe the degree and the leading coefficient. Well, what we know about the degree, if we look, this degree is going to be odd because my ends are going in opposite directions. So we know it's an odd degree. We also know there's 2 turns, so it has to be at least a degree of 3. The leading coefficient we know has to be positive because this type of end behavior has to have a positive leading coefficient. All right, so I know this has been a lot. It's a lot of new vocab as we get into this new unit. The last thing I want to look at real quick is just talking about an even and odd function. Now, this is something you're probably going to see a lot in pre-cal, but we talked about this briefly when we talked about symmetry for our cubic function. What's important to know is an even and odd function is not the same thing as whether or not the degree is even or odd. Okay, those are different things. So what we've been talking about up until this point is just what is the degree? Okay, so if a function is an even function, that means it has y-axis symmetry. If a function is an odd function, that means it has origin symmetry. So just because the degree is odd, it doesn't necessarily mean it's an odd function. It's a very specific function that is odd or even. Now, it's also very possible for your graph to be neither of these things. Again, it's kind of a special case, so it doesn't have to be either one of these. Algebraically, the way we determine it is what we do is we plug in negative x for x. If we plug in negative x and we get the exact same original function, that is proof algebraically that it's an even function. If we plug in negative x and we get negative f of x, which usually looks like the exact same function but the opposite sign, that is an example of an odd function. So what we do to test these is we plug in negative x. Well, negative x cubed is the same thing as just negative x cubed without the parentheses. And negative 7 times negative x would become 7x. Well, if you look, that's very similar to the original function, except every sign is different, which means that's the same thing as a negative f of x. So that is an example of an odd function. It also has an odd degree. All right, let's look at b. If we plug in negative x, I get the exact same as my original. If I get the exact same function, that's an example of an even function. Again, just because every even degree function is not necessarily going to be an even function, but you'll have some cases where they are. Because again, these are cases where they have a y-axis symmetry. But if you think about something like this, that has an even degree, but it doesn't have y-axis symmetry. So that even though it has an even degree, it's not an even function. All right, then let's look at this last one. If I plug in negative x, I get negative x cubed plus 2. Well, that's not exactly a negative of the entire function. It's also not the exact same. So this is neither an odd nor even function. Even though it has an odd degree, it's not necessarily an odd function. And again, this is something you'll probably look at a lot more in future math classes, but we wanted to introduce it here because we are talking about symmetry a little bit, but also because I want to make sure you guys understand there's a difference between an odd and even function and an odd and even degree.